In this problem, we're told to find the tension in the cable AB, which is right here, and the reaction forces at C and D. And what C and D are, they're actually bearings, one being a thrust bearing and one being just a regular bearing. So we're told that bearing C cannot support thrust, while bearing D can support thrust. So this problem is actually gonna be sort of like a lesson because I didn't know how to incorporate this idea or topic without actually doing an example. So what you can do, you can actually solve this problem by using vectors. However, I'm going to show you how to solve this problem using scalar operations. So the main trick in this problem is taking moments about one of these points, C or D. You could take either one because when you're in equilibrium, all points of this body should be, the rotation tendency of all points on this body should equal 0. So you could choose either point C or D when solving this problem. So you could use vectors to solve this problem, which is completely fine. But I'm going to show you how to do this using scalar operations, which involves projecting force vectors onto various planes, such as the ZY plane, or the XZ plane, or the XY plane. So that's what I'm going to show you in this video. The first thing we're going to do is draw out the free body diagram of this door. So we're told that the weight of the door and the rod is actually located at the center of this kind of square door looking thing. So we're going to draw the free body diagram of that. There's a tension cable being applied right here, and there's going to be reaction forces at these bearings. So I'm going to roughly draw this. So I'm going to roughly draw that. Looks sort of like a butcher's knife or something. Oops, that is not what I want. So something like that. So let me draw the reaction forces on this body, which shouldn't be too difficult. So what we were told is that the bearing D can support thrust, so there's going to be a reaction force pointing in the y direction, which I'll call dy, and these are defined arbitrarily because you could define dy going in the opposite direction. That is completely fine, as long as you're consistent with your signs and your orientation, which is already defined in our problem. As long as you're consistent with those things, the answer should be the same. You just may have to flip some force vectors at the very end. So what we have here, the bearing cannot move upward, so that'll be dz, and this will be dx. And then similarly, bearing C has the same thing except for this thrust force, so we could say that CZ, CZ, and CX. And then we have a weight force, which is being applied directly downward in the K hat direction, or in the Z direction, and then there's a tension force going in this direction. So what we're going to do is draw a tension force going that way. I'm going to define this angle as alpha, because as you can see, this is creating a right triangle. This distance is parallel with the x-axis, and this vertical distance is parallel with the z-axis, so we could say this is a right triangle, and this is going to be alpha. So this is how our free body diagram should look. So the first thing I'm going to do is to actually define that angle alpha, so we don't define it later. So alpha is actually the tan inverse of 0.250 divided by 0.2. I'm converting everything to meters, so this will be 51.340, although it doesn't matter if you convert meters here because the units cancel, which should cancel when you're finding an angle. So that is the angle of alpha. So what we're going to do now is actually start projecting vectors. So let me choose a different color. So we're going to project all these force vectors that are shown in this free body diagram onto the YZ plane. So let me draw the axes right here. So this is going to be X, this is going to be Y, and this is going to be Z. So the first plane we're projecting on is actually the YZ plane. So we're going to look at this plane. So just imagine yourself looking directly at this point or at this plane such that your eye is perpendicular to the plane so you can see it perfectly in view. You could choose either direction, but I'm going to look at it in this orientation. So what I'm going to do is actually draw the YZ plane. And how I define YZ, so let's see, this is going to be the YZ plane, so YZ, and YZ plane. How this is set and defined is that the first variable or first axis is actually going to be the horizontal axis, and then the z is going to be the vertical axis. So you say the horizontal, then the vertical axis, and then plane. So that's how I'm defining how I state these problems or state these planes. So what we're going to imagine is projecting or looking at the zy or the yz plane and projecting the vectors onto them. So I actually did not define this t vector. So what we're going to do is actually project those. So if you're looking at this butcher knife at this plane, what you're going to see is actually a vector going in this direction, which is tz, and also we're going to see CZ, DZ, and W, because W is pointing directly downward on the along the Z axis. And we're not going to see CX or DX because they're actually pointing at you, away from or towards you outside the screen, so you wouldn't actually see that vector. A quick tip is actually you can't see vectors or components of vectors that are not labeled on these axes. So for example, you don't see CX or DX because these they're not part of these axes. So you can think of it like that as well. So what we're going to do is project these vectors. So TZ is actually going to be right here. So TZ, this is going to be W, this is going to be CZ, and this is going to be DZ, and then there's going to be a dy going in this direction. So now that we have our vectors drawn, what we're going to do is actually perform our equilibrium equations on this diagram. So that should be fairly straightforward. So the sum of the forces in the z direction, that's going to be tz minus w plus cz plus dz equals 0. And that's just from this diagram that we just drew. So, and then we're going to do the sum of the forces in the y, which is going to be dy, and that's the only force acting in the y direction, so we know that dy equals 0. So although this bearing D can actually support thrust, there is no thrust occurring for this diagram. So dy is equal to 0. And then the next thing we're going to do is actually take a moment either about C or D. It doesn't matter because this whole body is at equilibrium, so no matter what point you choose, the rotation tendency of any point on that body should equal 0. So I'm just going to choose the moment about D just because I already did this problem before and already did the moment about D. So what we're going to do is take the moment about D, and how we define which way is positive is dependent on how we defined our axes in the problem. So if you look right here, we defined our coordinate system in this fashion. So if we do the cross product of y to z, we get a positive value pointing in the x direction. So it will be pointing along this direction, which is actually consistent with our diagram above. So that is important to know. So the correct orientation to define positive is actually going that way. So what we do is define that way as positive. Now if it was going this way, our x-axis would be pointing in that direction, which is not consistent with the right-hand coordinate system that was drawn earlier. So we want to define the moment as positive in this direction. So now I'm going to write out the moment equation. So what we have is 0.380 W minus 0.150 CZ minus 0.530 TZ, and that all equals 0. And if you're wondering how I get these distances, is basically finding the vector, let's say W. So I'm taking the moment about D, so I'm actually finding this perpendicular distance from W to D, the point D, and finding it on our original diagram. So it's W to D, so we're saying that this is W right here going directly downward. So I want the perpendicular distance from here to D, so it'll be something like that. So that is basically the moment equations that we're doing for this diagram. Now we're going to repeat the process for the 3 remaining planes. So the next plane we're going to do is actually going to be the XY plane. So the xy plane is going to look something like this. So let's see, let me make a darker green. XY plane, so look something like this. So this will be X, this will be Y, and this will be XY plane. And now we're going to project the vectors onto the XY plane. So the XY plane, that's actually, imagine yourself taking a bird's eye view of this diagram and imagining what forces you would see on the diagram. So what we'll actually see is this tx vector pointing in the negative x direction, because we defined x positive going in this direction. So we're going to see that vector, and we're going to see the vectors cx, dx, and dy. We're not going to see dz, cz, or w, because they lie on the z-axis. So what we're going to do, we're going to draw that projection right here. So what we're going to see is dy, this is going to be dy, this is going to be dx, this is going to be cx, and this is going to be tx. So it looks something like that. So just imagine you're taking a bird's eye view of the diagram and drawing it out. So now that we have that defined, we're going to apply our equilibrium equations again. So the sum of the forces in the x direction equal dx plus cx minus tx, which equals 0. And then we're going to do the moment about d once again, and we're going to define this way as positive. So let me go through that again. So our axes are defined in this orientation. This is x, this is y, and this is z. So we're looking at this plane. We're looking at this plane xy. So if we take the cross product from this direction to that direction, so imagine doing the right hand rule with your fingers, your thumb or your fingers are actually curling in this direction, and your thumb is pointing in the positive z direction. Since our thumb is pointing in the positive z direction, which is consistent with the diagram, then this orientation is the correct orientation for defining the moments. So what we can do is actually we're doing the same thing, but this is going that way and this is going that way. These two diagrams are consistent with each other, and this is positive. So that must be this turning tendency, which is defined here, is correct. So just make sure you're consistent with your right hand rule or right hand coordinate system. So once we have that, we could finish this moment equation. So this is going to be negative tx times 0.530 plus 0.150 cx, and that's going to equal 0. And we could do the sum of forces in y again, but that's going to be a redundant equation because the only forces acting in the y direction is dy, and we said that's already equal to 0 as shown right here. So we can write this again if you really want to, but it's not necessary. So the last plane we're going to look at, we already looked at this plane right here. We already looked at the xy plane. So the last plane we're going to look at is actually going to be the xz plane. So you could look at this plane either from this direction, like perpendicular to that direction. So like that, we could look at it in this direction, or we could look at it in this direction. But for this example, I'm going to go and look at it from this direction. It does matter what direction you look at. Just make sure you're consistent on how you draw your axes. So what we're going to do is draw from that direction and look at the projections by looking in that direction. So what we're going to actually see is this tension vector with this angle, and we're going to see CZ, DZ, DX, and CX. We're not going to see, we're also going to see W because that's pointing along the Z axis, but we're not going to see DY. So we're going to see every vector except for DY. So let me draw that right here. So the plane we're looking at is the XZ plane. So XZ plane, that's going to be that. So we're going to define it like this. So XZ. And then what we're going to do is actually draw the vectors being projected. So what you're going to see, if I could draw, so we're going to see a vector going here. And this vector actually composes of two different vectors. So I'm going to define it as dz plus cz. And then same goes along here. So that's going to be cx plus dx. And the reason why I'm combining these vectors, because if you imagine looking at this direction, which is parallel with this rod, you're going to actually see these vectors overlapping each other. So I'm just going to include them both together in one vector called cx plus dx, or cz plus dz. So that's just based on how we're looking at the projection. So this is just composed of two vectors. This is composed of two vectors. So now we're going to draw the tension force, which actually looks something like this. That's alpha, and this is going to be W, which is directly underneath where this tension force starts. So now that we have that, we can draw, or we could write our equilibrium equations. So the sum of the forces in the x direction is going to be cx plus dx minus t cosine alpha, which equals 0, and t cosine alpha is actually tx in this diagram. So then we're going to have the sum of the forces in the z direction, which is going to be dz plus cz plus t sine alpha minus w, and t sine alpha is simply tz. Now this is going to be the tricky part. So this is where I said you had to be consistent with your diagram. So we're going to draw a right-hand rule or right-hand Cartesian system right here. So what we want, we want to take the moment about D or C. It doesn't really matter because these are they lie in the same point. So we could say that the moment about D, and now how we define which way is positive is dependent how we defined our axes. So let's say we do the right-hand rule. So we do x cross z, or I cross k. What we're going to do is curl our fingers in that direction. So if we curl our fingers in that direction, that'll be the same as curling our fingers in that direction in this diagram. So if you curl your fingers in that direction, your thumb will actually be pointing in the negative y-axis. You don't want that. You want to be consistent with your diagram. So what we want is actually to curl our fingers in this direction. If we curl our fingers in that direction, what we get is that our thumb will be pointing in the positive y direction. So that is what we want. So we actually define positive in this orientation. So once we have that, we could write our moment equation, which is going to be negative t sine alpha, and all this multiplied by 0.2, and then we're going to add the weight, which is 0.2 times the weight equals 0. So now that we have all our equations, we can just solve this this problem by just solving the system of equations that are shown along here. So we have what, 1, 2, 3, so 3 times, that's 9 different equations to solve for all these vectors, and that should be more than enough to solve this problem. So what I'm going to do, I'm going to write out the equations that we need and actually write this the system of equations into a matrix form so I could plug this into MATLAB and solve this problem more efficiently. Well, before I write these equations, I want to say that Tx equals T cosine alpha, and that's just given in the diagram, and Tz equals T sine alpha. If you don't know where I'm getting that, let me just show you real quick. So this is actually the tension force going along the cable, and then Tz is just T sine alpha, and then Tx is actually just T cosine alpha, and this is going to be T. So that's where I'm getting that from, and I'm going to write these equations in terms of T cosine alpha and T sine alpha. So I'm just substituting Tz and Tx for these values when I write these equations. So these 5 equations right here should give us are the essential equations to solve all the components of this problem: the vector t, cz, dz, dx, and cx. So we have what, 1, 2, 3, 4, 5 different unknowns, and we have 5 different equations. So theoretically, we should be able to solve this problem. So what I'm going to do now is actually write these system of equations in a matrix form so I could use my computer to solve this problem. You could use any other method to solve system of linear equations that you think is sufficient for you. but I'm going to write this in matrix form, just plug in my computer because I am lazy. So if you guys are curious on how this matrix equation looks, so what I did is performed or put all the coefficients of these variables in this fashion, and how I place the coefficients in this matrix is dependent on how I define my variable vector. So I defined my variable vector in this fashion. So this should be, the first equation should be t sine alpha c plus cz plus dz equals w, which is here, and then 0 for cx plus dx, 0 for cx and dx. And then you repeat this process for the next row, and you should get this equation, and then so forth. So I'm going to use this and solve for the variables here, t, cz, dz, cx, and dx. So after plugging in this matrix equation, I solved for the variables t, cz, dz, cx, dx, and dy. And these are the answers I get. And you could write these in vector notation if you prefer. I'm just going to leave it like this because this problem is already cumbersome. So this is actually the answers that I get when plugging in this matrix equation. So to repeat what we just did, is the idea of projecting vectors onto various planes, and that allows us to do scalar operations to solve for various forces. And the most important thing is defining our orientations correctly when doing moments for each plane. So just make sure when you, for here, for example, we defined this rotation going counterclockwise as positive because it was consistent with our right-hand coordinate system that was defined for the problem. So if we cross, let's see, x cross y, so if we're doing x cross y, I just want to get this point clear. X cross y is going in that direction, so that'll be this in that diagram, which will be, your thumb will be pointing in the positive z direction, which is consistent with our right-hand coordinate system. So this is a valid definition for defining which way to rotate is positive. So that is that. And then to counteract that is this one. So we typically do this to define the positive orientation, but for this example we do x cross z, x cross c, so this is going to be like that. And if you perform the right hand rule, your thumb will actually be pointing in this direction, which is negative y, and that's not consistent with our right hand coordinate system. So what we actually had to do is define our orientation going from this direction, going in this direction, which is going to be this way. And if you do the right hand rule, your thumb would be pointing in the positive y direction, which is consistent with our right hand coordinate system. And then we could define that direction as positive. So that's probably the main trick in this problem. Make sure you know how to project vectors onto different planes. It's more of a visual thing, but through practice you should be able to understand how to do this quite consistently and fluidly. So, and then you just solve this system of equations, which is the most tedious part, and you could use either matrix, put this in a matrix format and then solve it using MATLAB or something, and then you get just these answers. So that's just a quick recap of what we just did. This is not too difficult, but you can also use this the idea of vectors using cross products and so forth if you find that is more simple. Just choose whichever method that is more easy for you and that you're more consistent on and less error prone for you. So that's just my spiel on things. So this is just a lesson / example for you to use and study for your statics course. I really need to stop talking like this.